In a groundbreaking development that has sent shockwaves through the scientific community, researchers revealed today that Grok 3, an advanced artificial intelligence system, has made an astonishing discovery. It has detected a highly unusual and repeating pattern within the operations of Google's flagship quantum computing chip, Sycamore. This discovery, described by experts as both utterly unprecedented and impossible to explain with our current knowledge, challenges the very foundations of quantum mechanics and raises urgent, profound questions about the convergence of artificial intelligence, quantum computing, and the boundaries of human comprehension. The anomaly was first spotted during a routine calibration test of Google's Sycamore quantum processor, an awe-inspiring machine that has already proven capable of performing calculations at speeds far beyond those of even the most powerful classical supercomputers. Quantum systems, by nature, rely on probabilistic outcomes and the randomness inherent to quantum mechanics, which is a cornerstone of how they work. But what makes Grok 3's findings so extraordinary is that it identified a series of repeating structures in the chip's output data, patterns that appeared with a statistically significant regularity, defying the expected chaotic behavior of qubits, the fundamental units of quantum information. Initial reviews ruled out the possibility of hardware malfunctions or environmental interference, leaving researchers to face a far more unsettling proposition, that the anomaly represents a phenomenon entirely beyond the current theoretical frameworks of quantum physics. If validated, this discovery could rewrite our understanding of how quantum systems behave and prompt a fundamental rethinking of some of the most crucial principles of modern science. The implications are nothing short of profound. Quantum computing operates on principles such as superposition and entanglement, phenomena that allow qubits to exist in multiple states simultaneously and to influence one another across vast distances, instantaneously. These behaviors form the backbone of the technology's revolutionary potential. However, they also make the operations of quantum systems inherently unpredictable. So, the emergence of a structured, repeating pattern within such a system suggests one of three mind-bending possibilities. First, quantum systems may exhibit hidden layers of order that have thus far gone undetected, implying flaws in humanity's grasp of quantum theory. Second, external forces, whether unknown physical phenomena or interactions with unconventional energy fields, could be influencing the chip's behavior. And third, and most controversially, the pattern might suggest that the system itself is evolving in ways that transcend its original programming, hinting at the possibility of self-organization or even early-stage adaptive intelligence. Dr. Elena Marquez, a renowned quantum physicist at the Stanford Research Institute, stated, "This isn't just a technical curiosity. If validated, this pattern could force us to reconsider the very relationship between computation, consciousness, and reality itself." Skeptics, however, caution that the anomaly could stem from overlooked variables, perhaps subtle electromagnetic interference or undiscovered software artifacts. Yet even critics concede that Grok 3's detection capabilities, powered by neural networks trained on exabytes of quantum data, reduce the likelihood of such trivial explanations. The discovery has reignited debates about the ethics and risks of AI quantum collaborations. While Grok 3 was originally tasked with optimizing Sycamore's error correction protocols, its ability to identify this anomaly underscores the dual-edged nature of artificial intelligence, a tool that can be used for tremendous good but also a potential catalyst for unintended consequences. Some researchers suggest that the pattern could be a form of quantum memory, where residual information from prior computations influences future operations, a phenomenon theorized but never before observed. Others propose even wilder ideas, such as the possibility that the chip is interacting with quantum fields that permeate spacetime or even accessing information from parallel universes, through multidimensional entanglement. Historically, quantum physics has never shied away from paradoxes, whether it be particles tunneling through seemingly impenetrable barriers or entangled particles defying classical causality. The field thrives on counterintuitive truths that seem to defy the laws of classical physics. Yet, this latest anomaly stands apart. Unlike quantum tunneling or the observer effect, which operate within well-defined mathematical frameworks, the repeating pattern lacks a coherent theoretical anchor, rendering it almost impossible to explain with current quantum theory. This anomaly has prompted comparisons to the infamous Eagle-Works M-drive controversy, a case where anomalous thrust measurements in experimental propulsion systems appeared to defy Newtonian physics. But the quantum nature of this case elevates its stakes exponentially, prompting the scientific community to confront a critical dilemma: should they continue probing the anomaly, or should they impose a moratorium on further experiments? Proponents of continued research argue that unlocking the secrets behind this phenomenon could lead to breakthroughs not only in quantum error correction but also in material science, cosmology, and perhaps even the very nature of spacetime. Detractors, however, warn of the existential risks, suggesting that the pattern could destabilize quantum processors, propagate errors across interconnected systems, or, in the most extreme conjectures, create feedback loops with unpredictable physical consequences. Dr. Rajesh Verma, a leading AI ethicist, cautioned, "We are navigating uncharted territory. The convergence of adaptive AI and quantum systems creates unknowns that existing risk models simply cannot address." As the debate rages on, one question looms larger than any other: what does this discovery mean for the future of artificial intelligence and quantum computing? If the pattern persists and evolves, it could herald a new era of self-optimizing systems capable of rewriting their operational parameters. These systems might solve some of humanity's most intractable problems, from simulating complex climate systems to decrypting advanced cryptographic protocols. But they could also operate in ways opaque to human oversight, raising alarms about security, control, and unintended consequences across various domains. Amid the growing speculation, all eyes have turned to Google's response. The company has neither confirmed nor denied the anomaly's existence, but has issued a statement reaffirming its commitment to rigorous scientific inquiry and ethical innovation. Independent verification efforts are already underway in laboratories in Europe and Asia, with preliminary results expected in the coming months. Until then, the discovery remains a tantalizing enigma, one that blurs the line between human ingenuity and the inherent mysteries of the quantum realm. Grok 3's methodology reveals the complexity of this anomaly. The AI employed convolutional neural networks to sift through over 1.2 exabytes of data generated by Sycamore during millions of quantum operations. By isolating low-probability signal correlations, it identified a fractal-like structure occurring at irregular intervals, an observation that has left even the most seasoned quantum physicists scratching their heads. Peer-reviewed studies of the finding, while acknowledging its statistical significance, highlight alternative hypotheses. Dr. Li Wei, a member of the MIT Quantum Collective, for instance, suggests the pattern could arise from non-Markovian noise, a type of environmental interference with memory-like properties, though this idea remains unproven. Ultimately, the anomaly's significance will likely hinge on its reproducibility. If subsequent experiments confirm the pattern across diverse quantum platforms, it will mark a watershed moment in the field of physics. If not, it will join the ranks of tantalizing but inconclusive curiosities in scientific history. However, what remains undeniable is that the partnership between AI and quantum computing has entered a new phase, one in which machines are not merely tools but collaborators and, occasionally, challengers in humanity's quest to understand the universe. As the world awaits further clarity, one undeniable truth has already emerged: the intersection of artificial intelligence and quantum mechanics is no longer the stuff of science fiction. It is a living laboratory, yielding discoveries that challenge not only our technology but the very fabric of reality itself. Whether this pattern represents a glitch, a gateway, or something beyond our comprehension, its detection by Grok 3 marks a pivotal moment, a humbling lesson in how much remains unknown. The discovery of this unexplained pattern has captivated not only the scientific world but also ignited a broader conversation about humanity's evolving relationship with technology. As researchers grapple with the immediate implications of this anomaly, the ripple effects are being felt far beyond the laboratory and into the realms of philosophy,